Welcome everyone. Today, this is the session 2 of learning CFD using OpenFOAM. And today we are going to learn about structured meshing using blockMesh dictionary. And to introduce myself, my name is Parish Palkar and I am working as a research assistant under the FOSSEE CFD team at IIT Bombay. And me along with my colleague Ivan and two more colleagues are going to be your instructor for this course. So for today, let us understand first what is block mesh. So has anyone done meshing here, or are they new to meshing? Or if you have done meshing but you used ANSYS meshing or maybe any other meshing software, is anyone there who has attempted at least doing meshing? Okay, okay, okay. There are a lot of people I can see. Okay, so you have done in ANSYS, Devansh. Okay, ANSYS CFX. Okay. So yes, as we all know, ki ANSYS is a good tool for meshing. However, we do have our own meshing documentation for meshing inside OpenFOAM. It comes with the installation of OpenFOAM, and that file is known as the blockmesh dictionary. So first of all, what is blockmesh dictionary? As we all saw in yesterday's session, blockmesh is a mesh generation utility. So it is a file that is provided by OpenFOAM, irrespective of the version that you use. Let it be 2412 or let it be OpenFOAM 9, or let it be from the ESI group or the foundation group, you will get a blockmesh utility inside your OpenFOAM. What does blockmesh do is it creates a structured hexahedral mesh with an aspect ratio near to 1. Okay, so aspect ratio is your minimum length upon maximum length inside your mesh, and generally we use blockmesh for generating structured mesh. Okay, uh, so if you were there in yesterday's session, our mesh, it is defined in mesh is written inside a folder called blockmesh dictionary that is located in your system folder. Out of 0, constant and system, it is written in your system folder, and the mesh is stored. So we are writing our mesh inside the system folder, and we are writing or we are contacting it with OpenFOAM and storing it inside the constant folder. In constant, there is a folder called polymesh. Polymesh stores the block mesh information or your mesh information in particular in terms of vertices, blocks, etc. There are 6 total files, but that is not of our interest as of now. Once we go into advanced meshing, we can dig deep down for this as well. And block mesh is generally used for simple geometries. Let us say if you want to make some simple cavity, or if you want to make a flat plate, or let us say you want to make a simple pipe. So for that we generally use block mesh. But to generate some advanced geometries, block mesh is used as a primary tool for generating the background mesh, and then we go for snappy x mesh for complicated meshes. As we all know, OpenFOAM is based on the finite volume method solver. So we cannot directly generate a 2D mesh. First thing, we have to generate a 3D mesh, and then we have to convert that 3D mesh to a 2D mesh. So let us understand what is the theory behind this block mesh thing. So block mesh, or to describe any square or a cube, it is just naming and points and coordinates. So we start by naming some points, and the 0th point of your cube is considered to be at origin, that is 0 comma 0 comma 0, and rest all the points are named according to the position. And yes, as I told ki it is a finite volume based library module, so we cannot generate 2D meshes. Firstly, we have to generate a 3D mesh, and then maybe using another library we have to convert it into 2D. And again, we have to name every point, vertices, and subsequently blocks that have to be named in the block mesh dictionary. It is just a file that we have to name, and one by one we will understand the file and format. Okay, so first I will turn on my uh, PowerShell. Just a minute, let me log in into my Ubuntu, then I'll zoom it. So as we know, the ls command is done for listing, and here we can see there are three folders. This cavity folder was something that we created in the yesterday's session. We copied the cavity case and we tried running the commands in this cavity folder. So the first command was blockmesh. So blockmesh is, as we know, in any cfd step, the first step is pre-processing. In pre-processing, we generally we create the geometry and mesh it. So today we are going to do the same. So let me go into cavity folder. So again, if we list out here what is inside the cavity folder, so there is the zero folder, there is the constant folder, and there is the system folder. So if I go into the system folder and list out what is in system, so there is a folder called blockmesh dictionary. So we are morely focused on this for today's session. Rest of all, we will get to learn a lot after once we progress. Okay, once we execute this blockmesh command, the mesh or the information that is being generated, it is stored in your constant system. So if you list out what is in your constant, so there is a folder called polymesh. This polymesh folder stores all of your information related to mesh. Okay, so if you again go into polymesh folder and list out, so here it is: boundary, faces, neighbors, owner, and points. So this polymesh stores every little information regarding your mesh inside a folder called polymesh. Okay, so first we will understand what is the format and what is the structure of the block mesh, and then we will proceed with how do we make our own block mesh. Okay, so again, to open this file using my file manager, I am doing explorer.exe. Yes, so now once I do explorer.exe, so I will open this file, and you can open your blockmesh dictionary using any. Let us say if you are using a gedit file editor, so you can do gedit system and then type the name of your file. So I have called my gedit in that of what I want to make changes, the system folder, and then block mesh. So you can hit enter and your file will be opened. But as I am more comfortable with VS Code, so I'll open my file in VS Code and then explain you everything. Okay, so let me turn on the VS Code first. I will drag and drop this file here and close. And as this is a C++ written language, so I'll just change this to C++. Okay, to dig deep into any open form file, we have to start from the scratch. So as yesterday we discussed what is form of open form, it is field operation and manipulation, and here it is said that it is written in the C++ format. Again, what is this open form? This is open form source CFD toolbox, and which version we are using. So for now, as of now, I'm using 2412. And what is the website of this particular installation? 2412 installation is given here. Okay, so once you open a open form file, it will look like this. Do not panic, it is very simple to understand. We will go one by one. Okay, so first thing here, uh, this is a form file. Okay, so this is the header, it is the form file. Which version that we are using? So it is version 2.0. And what is the format of this file? It is ASCII. We generally keep it ASCII. We never change it to binary. And what is the class of this file? So it is a dictionary. In dictionary you can make your changes, either it can be a dictionary or directory. So in dictionary we generally make changes and execute them on the terminal. And which dictionary it is? So it is the blockmesh dictionary. Okay, so first thing first, as this is written in C++, what you can do is you can, even if you are using gedit or nano, you can comment out whatever I'm telling to take notes. Okay, so the first parameter here is the scale. Okay, so scale is nothing but the points that we are defining in should be considered in which format. So let us say I keep my as open form understands only in meters. It takes your unit values only in meters. So if the scale is 1, then this unit system will be read in meters. Okay. And let us say if you divide it by 0.1, so every value that you are defining it here, so let us say this was 1 meter before, but now what will this become is 1 divided by 0.1, 1 divided by the point divided by the scale of your value, the value that you are defining here. It is just a scaling factor of which you want your geometry to scale down. Okay. So this is the first part of your scale. Second point is the vertices. In vertices, we define the point coordinates. Okay, so these are 8 point coordinates through which we create a hexahedral box. Coming down, so this is the block section. In this block, we name our block. Okay, so let us say there are 8 points here, and now we want to make it as a block. So here we name it using a hex. So here you can see the first point is your scale. As we saw, this is just a scaling parameter that we use to define our geometry. Vertices is something in which we define our points. Okay, so let us say there are 8 points. Please do not worry. I will explain everything in detail. There will be points. There is everything given in the PPT, so you can follow along with that as well. Okay, so just to get an idea what is inside this file, we are exploring this. So in the vertices section, we generally define the points. You can comment it out and write here, we define points here. So comment is something, if you have never done coding, comments are something that generally never gets executed in your function. It skips this part and it is for your understanding. Okay. In block section, we name the points or we create the hexahedral box that has been the of the points that have been mentioned in the vertices section. So here the box is made out of the points given in the vertices section. Okay, so here as we are going to make only a single block, so here there is only one block. I'll explain this, what is this. And edges, so if you want to maybe work on some curved related geometries, so for that you can use edges function, but it is a bit intermediate level, so we are not going to cover this today. And boundary, so if you are setting up any CFD simulation, so for that you have to define your patch names. In OpenFOAM, our boundary or the particular area for which we define our geometry is called as patch. So here we are doing nothing, but we are just naming that this particular thing will be my moving wall, which will be my fixed wall, which will be my front and back and everything. So let us say if you want to define your inlet, so you can just change this and you can define inlet here. Okay, and type and everything, we will get back to it later. Okay, so is the format clear of the blockmesh file? Okay, yeah. So it is a finite volume based library. We have to name every point inside your verticize section that we saw right now. And let us try doing a block. Let us actually try making a block. We can do multi-block as well, but for now, for simplicity purpose, we are going with a single block machine. So here you can see the dimensions. It is, let us consider this point to be at 0 comma 0 comma 0. So it is 2 meters in the x direction and 4 meters in the positive y direction. Okay, so if you can see, we will start by defining some small 2D plane section first. So as we know, let us consider this point to be 0 comma 0 comma 0. So this has been our point 0. Then we will go anti-clockwise. Okay, for naming we generally go anti-clockwise. It is a thumb rule in OpenFOAM or in blockmesh that you have to move anti-clockwise for naming your patches. Okay, so this will become my point 0, this will become my point 1, this will become my point 2, and this will become my point 3. Okay, so if we clip it to a 2D view, so in 2D view, if I saw in front, so what will this look like? This point is the projection here. So this will become 0, 1, 2, and 3. Okay, so these are, so this square block was the 2D section, 2D sectional view of this cube. Okay, now we are going to move to the next square block. Okay, the front patch, that is the 3D view that we have given. And please keep in mind again that we have to name it anti-clockwise. So, it is always better to start from the bottom. So this point will become 4, this point will become 5, this point will become 6, and this point will become 7. Okay, so if we see again in 2D planar view, so this point will become 2, 4, this point will become 5, this point will become 6, and this point will become 7. So if you saw, uh, earlier, what we did is we made a square section, and in the square section we named our points. Okay, so for a square there are 4 points, so we named them as accordingly. And what we did next is we defined the 4 more points. uh, the 4 more points were just only the projection of the previous ones with a particular thickness. Okay, so if you see, the 0th point is the projection on the 4th point, so the coordinates will be similar for 0 and 4, only with the thickness. Okay, if you can see, if you observe here, that each point on the first plane are the projection on the second plane with a defined thickness, that is marked in orange. Thickness, you can take it accordingly. It is not a constraint that we want a thickness of this particular size. So thickness is up to us. So if you see, the projection of 0 is done on 4, the projection of 1 is done on point 0.5, the projection of 2 is done on point 0.6, and the projection of 3 is done on point 0.7. So if this is the analogy behind naming the vertices. Okay, and let us now consider the points, again considering the 0th point at the origin. So the 0th point will become 0 comma 0 comma 0. The first point, as we are going 2 meters in the positive x direction, this point will become 2 comma 0 comma 0. The second point, as it is 2 meters positive in x and 4 meters positive in y, so this point will become 2 comma 4 comma 0. And then the third point, it is 0 in x but positive 4 in y, so this point will become 0 comma 4 comma 0. And again, all these points are similar. For now we have assumed a thickness of 0.1, so all the points of 4, 5, 6, and 7 will be similar, but only with the thickness of 0.1, 0.1, 0.1. If you see here, the 0.0's projection was on point number 4, so the coordinates are similar with just a defined thickness. Again, for 1 and 5, it is the same thing. The initial two coordinates are same with just a defined thickness. For 2 and 6 it is the same, and for 3 and 7 it is the same. Okay, so now we define them in our vertices section. So let me go to my terminal. So to save time, I have already created the case. Let me go to demo underscore 2 explorer exe dot. I will open this blockmesh dictionary here. So if you are able to see, again, this is the CFD tool kit box. It is 2412 version, ASCII format, blockmesh dictionary, and scale we are using 1 here. And now we have defined the same vertices that were discussed in this presentation. Okay, so see, all the points that were here are defined in this vertices section. Only the thing is, with a certain defined thickness, the points in the second plane are changing. So you can give your first point, give the coordinates and mark it as your first point in the comment section. So it will be better for your to remember what points are we using. Okay, so we have done nothing, but we have just defined points in this section. Okay, is it clear? Okay, so our two sections, that was scale and vertices section, is done. Okay, so in scaling we are not scaling our geometry, we are keeping it as it is. and then we are keeping our vertices to be similar, uh, of which we have discussed in this PPT. The This is nothing but just a projection of first plane on the second with a defined thickness. You can see the points here as well. The PPT will be shared to you guys, so don't worry about that as well. Okay, then we will come to the block section. Okay, so in this block section we define our hexahedral box. Okay, so for now let me go to my presentation first. And now to name our block, always start the naming using anti-clockwise manner. Okay, even we did the naming in the anti-clockwise manner, same we have to follow for defining our box. Okay, so let us say these are the two sectional views of plane number 1 and plane number 2. Both are 2D views. If you want to see, this is the first view, 0 1 2 3. This is 0 1 2 3. And if you want to see the second plane, this is 4 5 6 7, and this is 4 5 6 7. So this is just a 2D sectional view of the same block that I have taken, and we have to name it anti-clockwise. Okay, so what will be the naming of this section? This will become 0 1 2 and 3. Okay, similarly for the second block, this will become 4 5 6 and 7. Okay, so how we will write this as 0 1 2 3 for one section, and for another section we will write this as 4 5 6 and 7. Okay, if till this is done, what we are going to do is we will write blocks in the block section. We will define the hex, first hexagon, and we are just going to write all the numbers that we have followed. So the first four initial of these blocks are 0 1 2 3. So we have written it 0 1 2 3. And the second blocks naming, that is 4 5 6 7. So this will be 4 5 6 7. As of now, for simplicity, let us keep everything as 1. Let us not change anything. Okay, and for this patch as well, I will comment this out. Okay, so yeah, now our block is ready. Let us execute this command, blockMesh command, in our terminal, and let us see if we get any error or not. So I'll list out. Okay, so I'm in the right folder. I'll clear and I'll write block mesh. Okay, so now if you see my terminal, I'll just zoom out a little bit. So if you see, I have executed this command called blockMesh. So it has started creating the blockMesh. It is giving some warning, but it will execute the command irrespective of the warning. Then it will give you some basic statistics, key, which is the block, what are the faces, what are the points that are associated with this, and if there was any another polymesh dictionary previously. So let us say for this demo purpose, I already created this polymesh dictionary for you guys, so that we don't face any issues. So what it will do is, if we write blockmesh dictionary, it will previously delete the polymesh folder that was inside constant. So we are making a new mesh, and it is deleting the existing or the previous mesh that was present. Okay, and then it is saying it is creating the polymesh folder from the block mesh. Again, it is creating patches are nothing but the boundary condition that we have commented out as of now. Okay, we will learn how we can define them in some time. And with the scale value 111, so as of now we have given the scale value as 111. I'll define what is this as well. And these are the I, j and k vectors. Okay, so in I, it is 2 I cap, 4 j cap, and 0 0.1 k cap. Okay, so your block 0 with the cell size is given below. And if you have two blocks, if you want to coincide them, so we have to use the merge patch feature that is here. It is very complicated. We generally never go till that section. And then again, it is writing the polymesh. Then it will write the bounding box, as our block is starting from 0 to positive 2 in x, 0 to positive 4 in y, and 0 to 0 0.1 in z. The total number of points that were there are 8, as we have defined in the vertices section. There were 8 points which were here. How many faces are there in your cube? That is 8, that is 6. So there will be 6 faces in your cuboid. And how many cells are there? So there will be only a single cell. I'll show you. And if there are any internal faces, no, internal faces is generally used in snappy xmesh, so we will see that in later section. Okay, so patch names, we have not defined anything, so our patch number 0 with size 6, and the name has been default faces, and it has end the command. Okay, so now let us visualize it. How this will look like. For now, I have written this name as foam.foam. It is a good practice to write foam.foam so that we don't get confused. But if you are more comfortable with writing different name, so let us say I will delete this foam.foam, and let us say I'll again today, for today I'll write it as vit.foam. So now we have the vit.foam. This .foam file touch generally creates an empty file that we can execute. So we can maybe also do a touch vit.py. So as you can see, now we have a vit.python file. These files are empty files. If we write any Python command in this file and execute them, let us say I'll show you Python 3 vit.py. So it will not execute anything because the file is empty. So touch generally makes an empty file. And for our foam is we want to connect our openfoam data to paraview. For that we are using the extension .foam. Okay, so once I'll open my file and I'll open paraview, you can see here as well. Okay, this is vi double I, and this is vi, and this is Python source file, and that was paraview. So I will go in the file section, open, and then what I have done previously is, okay, I'll just copy the address of my file that is stored, and I'll paste it here. Okay, so now I have pasted the file location, and I'll do now navigate. Now .foam file will be identified with paraview, so it is showing. So I'll just click vit.foam and hit apply. Now, as our screen is a bit zoomed in, hence we are not able to see the geometry properly. Wait, what I'll do is negative x. I'll zoom out. Okay, so now the geometry should be visible. Okay, and if we go down, I'll turn on the axis grid. Axis grid generally tells you the dimensions of your file, and here we are switching it to the 2D mode. Okay, so now if you are able to see, wait, our x-axis is going from 0 to positive 2. That was our aim. Okay, now as we have zoomed in, so we are not able to see the legend, but if the screen was a bit zoomed out, you would be able to see the legend here as well. Okay, so as for now, our main interest was to create a block from going from positive 0, from 0 to positive 2. And again, in y-axis our interest was to go from 0 to positive 4. So as of now we have created a block that is going from positive 2 to positive 4. But in openfoam, if you want to visualize your mesh, you have to change this filter to surface with edges. Okay, and I'll close this axis grid. So if you see here, and I'll turn this to 2D 3D. So if you see here, we are not able to visualize any mesh. So there is a command here called here. So this section tells us how many discretization we want in the particular direction. Okay, so let us say you want to discretize your block 10 in 10 sections in x-axis, so you have to do 10 here. And let us say if you want to discretize your block in 20 sections in y-axis, So we will do 20. This is done. Now if you are able to see, there is no mesh, there is only a single cell that is present here. Okay, so now again I will save this file first, and I'll run blockmesh again. Okay, so it has run blockmesh. Now just on the similar file I haven't loaded, there was only a single cell in each direction. Now see, I will reload the files. Now see, so now our block has been discretized into 10 lines in positive x and 20 points in positive y. Okay, let me turn on the axis grid as well. So see here now, negative x, and if you count it, the number will be 10, and similarly for y axis as well. Okay, so this is the scaling, this is the parameter that we generally use. But then you might think ki, what is an ideal value? So a thumb rule is, generally what we do is, for 1 meter we discretize our block into 100 sections. Okay, so let us say now in your positive x the block is going till positive 2 meters. So what we will do is, we will discretize this into 200 parts, and in our positive y it is going till plus 4, so we'll discretize it in 400 parts. Okay, and save it. And I'll run blockmesh. It will take some time, and now the cells have been increased to 80,000. Previously, if you remember, the cell was only 1. Okay, now I'll just refresh this. See, so on now very fine mesh has been created, and this is generally the sort of meshes this sort of meshes are generally used in academia. Okay, uh moving forward, so as of now we have created a block, we have not touched simple grading or the boundary patch naming. So let us move forward and then see. So yeah, again, in the scale section, which units we are working, in the vertices section we define all the points that were present. In the block section we define the hexahedral box. Edges, if you want to use any spline or something, or maybe an arc, you can use the edges section. And we, for boundary, we define our patches here. Okay, so look at this block. So here we are defining the anti-clockwise manner of the block. So we define the hex block first here, and then we go 0 1 2 3 4 5 6 7, and this is hexahedral block. And again, this section tells us the desired number of cell values in x, y and z direction respectively. Okay, and simple grading is something that, let us say if you want a finer mesh in, let us say, x direction. Okay, so what we do is, we will just change this to 0.1, and for simplicity let us keep this to 20 and 40, so that our systems won't crash. So I am just changing now my simple grading to 0.1. I'll do block mesh again. So now the total number of cells is 800. We have significantly reduced the number of cells. Let me pull it back here. I'll reload. So now if you are able to see, previously the bias, if you are able to see, the bias was near positive x-axis. If we switch to a normal view, you will be able to see a legend. So in the positive x or the right section, uh, the positive x section is there. So if you want a finer refinement, or if you want a finer region in this section, so we generally give the simple grading as 0.1. So what 0.1 or simple grading does is, it is the ratio between your first cell to the last cell. Okay, it is just discretization, but the ratio between first and last cell will become 0.1. Okay, so let us say you have done in positive x, but if you want to do a simple grading in positive negative x, so you have to just change the symbol of simple grading sign. I'm doing negative x, and now I'll run blockmesh again, and I'll refresh my file. So now see, so the ratio of first cell, this first cell to this cell is 0.1. Okay, So it is generally we generally use simple grading whenever there is a flow separation or we want to capture some large eddies. So in that section we generally use simple grading. For initial learning purposes it is okay if you skip that as well, but let us say if you give zero point 0.1 as zero point 0.1 in the positive y direction as well, so what will happen is, and I'll refresh now. If you now before I'm telling ki there will be some refinement in this section as we are in the positive y. See, so we have done refinement in the positive x and positive y. So let us say there might be some inlet here and it was injecting some fuel from this end. So if you wanted to capture this area very accurately, so we generally do simple grading in this section. Okay. Moving forward, we have seen about the x and y direction, but as of now we are not sure what is happening in the z direction. Okay, so if you are able to see, the z direction is only having one cell. That represents that we are not going to solve anything in the z direction. Okay, so see here also in our file as well, we have defined the z direction to be 1, and likewise here as well, the z direction is having only a single cell. So we are not interested in the z direction. We are just see this is the z axis and we are having only single cell. So we are only going to solve for x and y. If we run any simulation, this is a way to generate 2D meshes. Okay. And yes, so if we increase the simple grading value, then the aspect ratio will keep hampering. Okay. So this is the grading system. So let us say we are doing in negative x. So this is how it looks in this is negative grading looks like in negative x-axis, and this is what positive grading looks like in positive x-axis. Okay, these are just numbers that we have defined in our block mesh. So don't worry if you are not able to understand grading. You will understand once you go into bit details of block mesh. I'll share some documentation as well for this. Okay, so yeah, so as of now our single block structure was done. So we have created a successfully single block. Uh, so before moving further, do you guys have any doubt? So we have covered single block meshing using single block. Now we are going to move for the multi block meshing. So if you have any doubt, please you can ask. Okay, then shall we start with multi block meshing? Can we do grid? Yes. So this is a very uh, very important question, that can we do grading in both positive and negative x direction? Yes, you can do positive and grading in both positive and negative direction, but it will hamper the quality of your mesh in the center region. Okay, how to make finer mesh elements on both ends. Okay. Okay, so this comment I'll show a documentation how to do that, because if I do it here it will take some time. Okay, so you have to define it. I'll show you. No problem, this is a very important question. I'll address this. Any other question than this? Okay, so let us start with multi-block meshing. If anyone has any question, you can put it in the chat box. I'll try to take them. Okay. So now we are going to the multi-block meshing. Multi-block meshing is very important. You have to keep in mind that we maintain connectivity. So if you are able to see now, this is a L type structure. Okay, this is a L type structure. Now here, what we have to do is we have to consider this point at 0 comma 0 comma 0, that is origin, and then proceed accordingly. But you have to maintain the connectivity between the blocks. Okay, what I am trying to say is, we'll understand with the pictures. Okay, so what someone might think is that I'll create one block in the positive x direction, and from this point I'll extrude it in negative x and again go positive y. So this will not work, as there is no connectivity between this point to this section. So you have to maintain connectivity between every point. So let us say you are starting from here. So we will do uh, one block section like this, then we will extend it to the positive x, and we will do similar with positive y. Okay, so there will be three blocks. As of now we have just done a single block, that is the red box that we did right now. You can see we have just created a single block. We have just created a single block, but if you want to do a multi-block meshing, so we have to create three blocks into it. Okay, so let us go forward. Just try keep this in mind ki all of your points are connected. If you are making any point, then make sure that it is connected to the other. Okay, so this is the orthogonal view of the multi-block, how it will look in 3D. So this is your 0 point. This is the same point that, okay, is there any comment? How to get finer mesh important boundary? Okay, okay, I'll address this question. Uh, this was the block that we have defined previously. If you remember, this is the same block. So if you are able to see, this is the same block that we have used in this section. We are just going to build on this. Okay, so this is the same block that we have generated with some different boundary parameter. Earlier it was positive 2 in x and positive 4 in y, but now we are going further. So there will be one block in the positive x section and positive y section as well. So if you see, there were 2 points already. The block was already created with 8 points, and through this from this section we have extruded a box again. We are already having 4 points of this block, and now only more 4 points will be added, okay, in this section. So this new points are marked in yellow, if you are able to see. Okay, so the same approach has been taken here as well. So we have just, the previously four blocks were there, and we have just extruded it in positive y upwards, and the naming has been done likewise. Okay, and it has been colored in different way, so that you understand ki this was the first block, this is your second block, and this is your third block. Same way we defined, this is our first block, this is our second block, but the points and coordinates here will be similar. uh, this will be intersecting, this will be sharing, this will be doing the point sharing, and same for this as well. So this is done. This is the orthogonal view, and same for as we have extruded in positive and positive x. So yeah, I mean, let us now, we have to just define the point coordinates. We have done 1 to 8. Now we have to just define 8, 9, 10, 11, and 12, 13, 14, 15. Okay, so for that also I have a tutorial with me. Okay, wait. System blockmesh. Meanwhile, I'll delete all these files. Okay, C, C++. I'll delete my systems as well. Okay, so as we can see, again, if you see, there are 15 points. So isn't the naming wrong for 8, 9, 10? Okay, I will get back to this. I'll get back. So this is scale. We have defined scale 0, and till this point we have done everything in the previous tutorial as well. Now we have to define 8, 9, 10, 11 points only. So if you see, what your points will be, will we have to define them anti-clockwise only. So this will be your 1, this will be your 2, this will be your 3, and this will be your 4. Okay, so if try to imagine in this way, so this will be your 1, this will be your 2, this will be your 3, and this will be your 4. So we have created a hexahedral block for this section, and same for the projection part or the front plane with some certain thickness. So this part will be your 5, 11, 10, and 6. So your total hex block will become anti-clockwise naming of first four and anti-clockwise naming of the projection. So this will become 1, 892, 1892, and 5, 11, 10, and 6. 5, yeah, there is a typo. So this will be 5, uh, 11, 10, and 6. Okay. And similarly, for this section as well. So if you are able to see, we have defined it correctly here. 5, 10, 11, and 6. So this is just a typo. Okay. And same for the upwards block as well. These block, just try to focus on these blocks, and we have extruded it upwards. So this will become, the front patch will become 3, 2, 12, 13, and the projection part will become 7, 6, 14, 15. So this will become 3, 2, 12, 13, 7, 6, 14, 15. Okay. So we have done nothing, but we have just defined the points, that is 8 point, 9 point, 10th point, 11th point. Just keep in mind ki whichever projection is there. So let us say this 10 and 11 points are projection. So we have added thickness to it. Okay. I have added two new points, and then I have added the similar points with two new thickness, with same thickness. Okay. And similarly for these points as well. So I have added two new points, and then I have added thickness to these points with thickness. Okay. And initially we have defined this block. Okay, so we don't have to see this block, we have defined it, no problem. Again, if you want to do multi blocks, you have to just keep on adding your name of your block into this section, and it will be done. So right now we are doing three blocks, hence there are three sections, hex section. So first hex section is the singular block that we made previously, that was 0, 1, 2, 3, 4, 5, 6, 7. And our next hex section is this end, the smaller, on the positive x. So our x will be this. Just there is a typo. These 2 points are mismatched. There is a match, numbering error. Okay, this is typo. Please do not go on this. The correct format is given in this code. Okay. So I'm just copying this file and just pasting it here with the number of cells that I want in XYZ direction. And for now, to keep the uniform mesh size, we are going with simple grading as 1. If we keep simple grading as 1, the our mesh that will be created will be uniform. Okay. Similar for this upward section in positive Y, the hex block is defined here, and we are naming it anti-clockwise. So it will become 3, 2, 12, 13, 7, 6, 14, 15. 3, 2, 12, 13, 7, 6, 14, 15. Again 3, 2, 12, 13, 7, 6, 14, 15. So this is done in the third block with 20 cells in the X, 40 in Y, and 1 cell in the Z direction. As we are generating a 2D mesh, we are not interested what is happening in the Z direction. So we are going with only 1 cell. We cannot keep it as 0. As we know, it is a finite volume based library. So it will need 3D locations, 3D mesh generation. So for that, we are going with only 1 cell. Okay. And as of now, we have kept the simple grading as 1, but if you want to explore more, you can change these values here as well. Okay. And now I will just run this till this section. I'll just comment this out. Okay, so every part is commented now, and I'll go to my terminal and I'll just run blockmesh here. I have to come, and I will do blockmesh here. Wait, no, just do blockmesh. Okay, so it has done meshing. Previously the scale was 111. There were three blocks. The vector values are given here. Okay, block 1, block 2, block 3. Then the stats key, there are 1600 cells. What is our bounding box? Bounding box is your background mesh. More about this background box will be understood when we learn snappy x mesh. Okay. So there are these number of points in your cells. As we have discretized our domain, there are 6500 faces, and there are 3100 internal faces, and every patch has been kept as dumped in default faces. So now we'll do ls. I have again created a foam.foam folder here. So I'll open it. I'll delete this vit foam. I'll open I'll just go one step back. Here I have all my folders, demo 2, demo and cavity. So I'll go in demo, and this is my foam.foam file. So I'll open this and hit enter. So if you see in negative x, let me pull it down. So it has created an L size L shaped domain. Okay. L-shaped domain has been created with the help of three blocks, that was 1, 2 and 3. And if we turn it to surface with edges, so if you are able to see, we are having a very finer mesh in we are having a uniform mesh, not finer. A uniform mesh is what we are having in this section. And if you zoom down in this ribbon, so there is a filter called mesh regions. So in the mesh regions, there will be an internal mesh that will display the total mesh that you have. And let us say if you want to find out any new face, so it will be added here. So let us say you define inlet, outlet, walls, top, bottom. So everything will be defined here. So as of now, as I have commented out everything, so there is nothing here. But once we define the patch names, the patches will arise here. In default faces, if you hit apply, whole of your geometry will come, as everything has been stored in your default faces. Okay, so now let us move further. As we have defined the patches, now just we'll just go how we can define the patches. Okay, I'm not going to define every patch. I'll just teach how to name one and two patches, one or two patches, and then it is pretty much self-explanatory. Okay, so if you try to see this block in a 3D section, okay, from this end, okay, let us say we are watching this block from the left hand side view. So what will it look like? This will look like an two box section with red box in the bottom and the pink box in the upward section. So these are the same points that we have used in this area, and the 2 points. Okay, so again, if you are watching it from the front side, it is very easy to name them. Again, you have to name the points and faces here in the anti-clockwise manner. Okay, so the points here will become 0, 4, 7, 3, and for this patch it will become 3, 7, 15, 13. Okay, so let us say you are working on any simulation that water is coming at high velocity from this end, and it is leaving from this outlet, as this is working as a pressure outlet. So you will define everything in this patch. Please do not make a mistake that as this is a single block, I'll just name 0, 4, 15, 13. No, as this is consisting of two blocks, we have to name them differently. Okay, so this will be the patch name. We are going with inlet, and there are multiple patches. So if you want to have a boundary condition, then we generally go with patch. If you want to have this as walls, so there is also a function called walls. You can add this. Let us say if you are working in a 2D simulation, then this will become empty. Okay, for z direction. And in that inlet section, we are just defining the faces in the anti-clockwise manner. So coordinates of the hexaedral box that we have seen here, so we have defined the first section in this way, and the second section in again in anti-clockwise manner. And now let us try to visualize this box. I am going to name this as outlet. This is we are watching from the right hand side view. So if you see, now I have defined it as outlet. This, as we are going to assign a boundary condition to this particular patch, so it will be used as boundary condition patch. If you see from the front, this will become 10, 8, 9, 11, and same we have added it here. Okay, what will I do is I will submit all these files, so you can check it out for yourself. Okay, front, back, and so I'll uncomment everything. So see, this is the inlet patch, this is the outlet patch, this is the bottom. Again, we are going with patch. Top, I don't want my simulation to get interrupted with my top faces, so I am defining it as walls. And again, same, if you are watching it from upper section, so I am going with top for 15, 14, 12, 13. So this will become 15, 14, 12, 13. And let us say I want to define this patch as my wall, so I'll watch it from the front view, and this will become 6 to 12, 14. 6 to 12, 14. And again, let us say if I want to define this patch, then it will become 6 11 9 2. 6 11 9 2. So we have to just name them anti-clockwise and dump them into the faces section. Okay. And let us say, as we are working on a 2D simulation, so the front and back will be the empty faces. So now if you want to name the front section, so it will be one red section, one red and yellow section, and one red and pink section. So let us define the red section as front section, the projection plane. So it will be 4 5 6 7, 4 5 6 7, and the intersection of red and yellow, so it will become 5 10 11 6. This will become 5 10 11 6. And let us go upwards. So now if you are watching it from the front side, then it will become 7 6 14 15. So it will go 7 6 14 15. Likewise, we are going to do for the back patch. So that is the of which the projection we get on the front plane. Likewise, we are going to do with the back patch same 0 1 2 3 1 8 9 2 and 3 2 12 13. So 0 1 2 3 3 2 12 13 1 8 9 2. So we have defined our patches. We can save this. We can run the blockmesh command. Okay, so now our simulation has been, our mesh has been carried out, and now here is some interesting information that has been dumped. So our patch 0 is inlet, patch 1 is outlet, patch 2 is bottom, patch 3 is top walls, patch 4 is front, and patch 5 is back. Keep in mind that we have utilized every cell that was present in our geometry. Hence there is no section called default faces. If we by mistake miss any section for naming in this section, let us say we leave one face, so that will be technically and on its own will be dumped in patch number 6 called default faces, and it will be added here. Okay, so now here the mesh has been run. The total number of elements are also given. Key for inlet patch 60 cell size has been distributed. For outlet there are 20 faces. For bottom and top there are 40 and 80 respectively. So likewise we can do. And once I will do refresh, so now if you are able to see in the mesh region, it was empty. As this is not reloaded, I'll reload this file, and now it will take some time. As I have clicked the default faces, so it will not show anything because there is nothing in default. So to switch on my mesh, I'll just click internal mesh and hit apply. See, a total hexaedral block has been generated. Okay, and if you want to specifically see how the inlet patch looks, how the outlet patch looks, we can do that as well. So we will just click inlet and we'll just click outlet. Where is it? Outlet is at bottom. We'll hit apply. So see, our inlet and outlet both patch has been defined, and we have filtered it out separately. Let us say if you want to view something extra, let us say we'll go with the bottom patch. So now you are able to see the bottom patch here. If we go with the top patch, top will do a horizontal line, a straight line, and again a connecting horizontal line. See, so this is a basic 2D view or the outside view. And if we turn on the front and back patches, so this will give you your front face and back face as well. Okay, so we have got our mesh. Keep in mind this is watertight, meaning that water cannot go out, go away from this. This is a watertight geometry. We are just using a filter to view our patches. Okay, and let us see if I hit default patches and unselect everything and apply, there will be nothing. As we have selected every other patch of our region, there is nothing stored in default faces. Eventually it is the process of paraview that it stores the information. But I'll again go to my internal mesh, as internal mesh will display everything. This is the mesh that you will generally work on, but if you want to separately view your mesh, you can do this filter operation. Okay. Yes, and yeah, I mean, that's it for today. You have an assignment, of course. Uh, so, yesterday, what we did was we copied a case. and we tried running it in our run directory. Today we are going, so for you, this is the assignment. So you have to consider this block at 0 comma 0 comma 0, and this will go in positive x 9 meters, 3 meters in positive y. Then this block will again go backwards and it will form a T-shaped junction. All the respective dimension sizes are given here. You have to just ensure that there is no imbalance in the connectivity. Okay, so for now I am giving you hint as well that there will be four boxes here. Okay, so you have to make four boxes, mesh them, allot the points, mesh them, and do your assignment. Okay, so yeah, that's it for today. But these are very simple blocks. I mean, in OpenFOAM or in CFD simulation, you cannot go with very complicated mesh system setups using blockmesh. So for that, we have to use Snappy X Mesh dictionary. It is a bit complicated, but using Snappy, we can generate some complicated meshes as well. It is a bit tough, but just stick along with me, and I'll try my best to help you out. Okay, and yeah, thank you.